Okay, I think it's back. All right, good morning, everyone. Sorry for a little delay there. All right, today we're going to talk about approximation algorithms. Before we get into approximation algorithms and how do we measure the success of our approximations, I'd just like to put this in some kind of context, the context being that of the previous lecture. So if we recall this picture, right, these reflected two different models. Depending on what you believe about P equals NP. The model on the left reflects probably the more widely held belief that P is not equal to NP, which means we have a lot of problems outside of P, and some of those problems are NP complete problems, as well as NP hard problems. NP hard problems include both problems that are unsolvable, provably unsolvable, as well as problems that are more difficult than NP complete. We talked about some examples of those last time. We have another model. The other model says that P equals, P equals NP. If P equals NP, then all the problems that are in NP complete, which are part of NP, are also part of P as well, which means all the NP complete problems can be solved in polynomial time. I repeat, according to this model, all those NP complete problems can be done in polynomial time if we believe this model. Again, I think most people believe this model is true, but remains to be seen, maybe in our lifetime. All right, so just another review before we get into the approximation algorithms. If we want to prove that a problem is in NP complete, all right, we need to do two things. First of all, we need to prove that it is in the class NP, which means either that we have a non-deterministic algorithm to solve it in polynomial time, or we have, if we're given a solution, we can verify a solution in deterministic time, deterministic polynomial time. That's usually the easy part. Then we have to prove that the problem is an NP hard, which means it's at least as difficult as the known problems in NP complete. And we use a polynomial time reduction, which basically says, take this problem, show that it can be thought of as an instance of another known NP complete problem. And since we know we can't solve that, it must be we can't solve this one either. All right, the question is, can NP complete problems be solved by supercomputers? So the answer is yes and no. What does a supercomputer do for us? A supercomputer can increase the number of operations per second. So instead of billions, maybe it's 10 billion or 100 billion, but it's not going to. Think about that slide that it had on at the beginning of the semester, then had it on last time, right? That if you take your n squared algorithm on a billion pieces of data, right, it takes 65 years, I think, 61 years, 65 years, right? So let's just say that your supercomputer is 100 times faster, 1,000 times faster, right? So now your 61 years is going to go down to 1 year, or maybe a tenth of a year. Do you really want to sit there for a month or a year waiting for, your supercomputer to finish sorting your Facebook users? By the time you're done with that, the number of users is going to change. So supercomputers, yes, they are much faster than other computers, but they can't solve NP complete problems in a reasonable amount of time either. All right, so again, we have lots of NP complete problems. This is just a small subset. These are some of the most famous ones. And now we get to approximation algorithms, all right? So here's the issue. The issue is we have all these important problems in computer science, practical problems that arise in industry and every area of human life, and we need to solve them. But to try to solve them optimally, we don't know of a deterministic polynomial time algorithm. So what do we do? So there are different approaches, right? One approach is, you get better hardware, and that'll help a little bit, but it's not going to help that much, right? You can try to use distributed computing, but you're going to need a lot of computers to do that, right? So if it's exponential time, and you have good speed up, it's still going to be expensive. So another approach is to say, you know what? I don't necessarily need the very best answer. It's good. It's okay to get an approximate answer. So I remember when I was still in high school, and I had a friend who was in a very good engineering school. And he said that what he needed to learn when he got to engineering school, college, is that you don't have to do all the homework because there's just not enough time to do all the homework. So you need to figure out what homework is most essential, because you just can't do everything in the amount of time that there is, right? So approximation algorithm is sort of like that. It says, I can't do all the operations I really need to do to get it perfect. What do I need to do to get it close to perfect? All right, that's sort of the idea here. All right. So particularly when we have an optimization problem, right? We're trying to find the maximum way of doing something or the minimum way of doing something, and we can get, 80% of the way there or 50% of the way there, whatever the percentage is. So maybe that's good enough. We have to be a little bit more careful with the decision problem. What do we mean by a decision problem? Can someone write an example in the chat of a decision problem?
0-1 knapsack problem?
Well, not by itself. Now, we need to qualify that a little bit. So yes, there is a decision version of the 0-1 knapsack problem, but the 0-1 knapsack problem by itself is an optimization problem. So what does it mean?
What about decision trees?
A decision tree is a model. It's not a problem. Let's go back to the knapsack problem. How do we convert the 0-1 knapsack problem into a decision problem? So here's how you formulate. You say, can I get $100 worth of stuff into the knapsack? Okay, you see the difference? We're not saying what is the maximum amount of stuff I can get, maximum amount of value I can pack into the knapsack. That's an optimization problem. That's this. Decision problem says, can I get at least $100 worth of stuff into the knapsack? It's a yes or no question, right? Traveling salesman problem. Can I visit all the cities once, come back home with a cost of less than 1,000? That's a decision problem. Optimization problem would be, what is the minimum cost to visit all the cities exactly once and return home? See the difference? So decision problems are generally actually easier, because we saw that last time. NP hard would be to actually maximize traveling salesman problem, minimize traveling salesman problem. The decision problem is only NP complete. All right, so once we have an idea for an approximation algorithm, we can ask ourselves the question, well, how good is it? How close to the exact answer is it? All right. Meaning, if we took a computer and we let it work forever and come up with the optimal answer, how far off, for better or for worse, would our answer be? So we have three measures that we're going to explain to you here. The first one is what we call the absolute error bound, which says, let's assume that C star denotes the optimal solution, and C of n represents the solution or the cost of the solution that your algorithm found. So we take the difference between them and we say, we don't say, we try to find out what do we know about that difference? Is that difference going to be 1, 10, 1,000? How close to the actual answer am I going to be? And then we can decide, is that close enough or is it not close enough? So I want you to observe the following, all right? So E is like your error function, all right? Generally speaking, we make the error function a function of n as opposed to a constant. Why? Because it's reasonable to say that the bigger n is, the bigger the size of the problem is, the more error we expect and the more error we're willing to tolerate, right? So if your n is 10 and you get an error of 100, that's a pretty bad error. But if your n is 1 billion and you get an error of 100, meaning you're just 100 off from the optimal answer, you know what? That's not so bad. Okay, so we call that an absolute error bound. Then we have a ratio error bound, and as you can see, we're dealing with a ratio. We take the ratio between the optimal and the non-optimal, and depending on whether it's a minimization problem or maximization problem, that determines whether we put the optimal one on the bottom or on the top. And once again, we say that it should be less than some kind of error function, right? Where again, depending on the size of the problem, we would allow for a bigger error, right? The third approach, which is a combination of the other two, is what we call a relative error, right? We're saying take the difference between the optimal and the algorithm one, take the difference, divide that by the optimal, and that's a relative error, right? So in all these cases, we're saying, what does your algorithm give you? What would the algorithm give you if you went all out and you found the exact answer? And you look at that number and you compare the two. You compare them in different ways, by taking the difference, by taking the ratio, or you take the difference over the original number, compare that to something and say, is that acceptable or not? Sometimes it is, sometimes it isn't. But approximation algorithms, before we get into the specifics of the approximation algorithms, are very important because we cannot depend on exhaustive search, brute force for these exponential, kind of problems, right? Did someone have a question?
Yeah, how do we get the optimal cost? Isn't the whole point that would take too long to do an exhaustive search?
All right, so that is a very important question, very good question, right? It shows you're paying attention. The answer is, well, you can try it. So, okay, first of all, the way this usually works is, some very smart people who do research, they will mathematically prove how far off it's going to be. Okay, so you can do it what we call analytically. Okay, so there's usually some proofs. They're usually, pretty involved. We're going to do one, which is sort of a fairly straightforward argument, but there are more complex arguments that are offered depending on what it is. The other thing you can do is sometimes you can test it, right? So you can, take a bunch of scenarios and you do empirical testing. So when we've done a lot of empirical testing in this class, but it's mostly been about time, right? How much time do the different algorithms take? You can also say, okay, we're going to take some smaller cases, and we're going to, figure out, what would the optimal answer was for this smaller case. Look at what our algorithm does and see how we do. So it's almost like an approximation to the approximation, right? We're saying, in our test, we found that we never got more than 50% off. Okay, here's something else that I've done. Okay, so last summer, in the winter course, I taught this course for the first time in a winter session. So we did a bin packing problem, and you know what I did? I created a scenario that would fit exactly into a certain number of bins. So I knew exactly how many bins. Then I shuffled the data around. And I said, okay, you use the approximation algorithms that I'm going to teach you today, and I taught them, and use those algorithms and see how you do. So I know exactly what the right answer is. That's my point here, right? You can construct examples where you know what the right answer is, and then you say, okay, how does your approximation algorithm do? So that's another option. But you're right. Sometimes we don't know, and we'll see that some of these error bounds are actually approximates, right? We know that it's not more than 1.5 off, but we don't really know how close to that it gets. So yes, that's a fair question. All right, so these are 3 examples, and I have one more. Okay, so what was the question here? What was the question? How we get the optimal solution if we're saying 7 people? Exactly, yeah. Okay. All right, so we're going to look at a bunch of NP-complete problems and some approximation algorithms. So you start to get the feel. Again, each problem has its own kind of approximation algorithm, but you sort of get the idea of how we do this. All right, so the problem we're going to spend the most time on today is the bin packing problem, or BPP for short. And we sort of mentioned this yesterday, right? And again, there are many variations of the problem. The simplest variation is to assume that our bins are all of the same size. Okay, for example, they have a capacity of 1. And you have items. So obviously any item that's bigger than 1 is not going to fit in a bin, and we can't solve the problem. We're talking about where we have items that are smaller than 1, right? The cost, the weight, the size, whatever it is less than 1. So the question is, how many bins do we need? And like most of these problems, we have 2 versions of it. We have an optimization version, decision version. Optimization version says, of these n items, what's the minimum number of bins do I need? Do I need 5? Do I need 10? Do I need 100? How many bins do I need? And then we have the decision version, which says, I don't need to know the exact number. I want to know I own, right? I'm a shipping company. I own 10 bins. I own 10 trucks, right? Is that going to be enough? So that's what I really want to know. Keep in mind that, I got to figure out how to get it in there. All right, so these are some questions. I'm sorry, I didn't understand. Changli, what's your question there? Didn't understand the question. Okay. So we're going to talk a little bit about upper and lower bounds in a moment. Actually, let's do that right now. Okay, so can someone give me an upper bound? If I have n items and the capacity of each bin is 1, what is the maximum number of bins I need?
N bins.
N bins, right? In worst case, each item, we said that all items have to be less than 1, otherwise it's completely unsolvable, less than or equal to 1. So the max that I would need is n bins, right? You put each thing in its own bin. All right, what's the minimum I need?
1.
So 1 is a minimum, but can we get a better lower bound? You don't need any fancy algorithms for this. Well, we want a better, we want a better lower bound. Better means closer, not lower, but closer to the real answer. Okay, let's take an example here. Let's say that it turns out that all my items are 0.5, and I have n items. How many items, how many bins do I need? So if n items, each of them is 0.5, how many bins do I need?
N over 2.
N over 2, correct. Okay, so what I can do is I can add up the weights. I have n items, sum up their weights, and let's say it came out to 11.8 was the sum of my items, the weights of the items. And the capacity of each bin is 1 pound. So how many bins do I need?
12 at minimum.
12 is my minimum. So that's a better lower bound, right? So yes, 1 is a lower bound, 0 is a lower bound, -1 is a lower bound, but those are not as good as informative as a real lower bound, right? So if I take the total weights and we're assuming a uniform capacity, so or divide by the capacity, which is 1, right? So that, and I round up because I can't use a half a bin, right? A half a bin is a bin. All right, so that's a lower bound, right? So somewhere between the sum of the weights and the number of items. Okay, now when we talk about bin packing, we have 2 versions of this, and I introduced these terms to you back at the very beginning of the semester when we talked about sorting, and I said that all the sorting algorithms that we are going to do are offline versions, but I did say that online will come back, and here it's coming back today. So an offline version means we have our n items and we need to pack them. The online version says we don't have our items, they're arriving as we speak. So imagine you have an assembly line of trucks, right? and you're getting the items coming out of the factory or the distribution center. You need to get them into the truck. So you don't have all of them. You can't sit there and do a whole algorithm on everything that you don't even know yet is going to be produced. So you got to deal with the stuff as it comes out, and you have to decide, okay, I got 5 trucks there. I can put it in any truck that's there, but I still don't know what's coming. I can't try to reconfigure everything. So it's a more difficult problem than in the offline, where I have more possibilities available to you. Right, so we're going to look at both of those problems here. So this is what we were just discussing. The initial bounds, obviously the maximum number of bins is n, right? If each bin is uniform size and each item is no bigger than the size. So in worst case, we put each thing in a bin, but the minimum number, a good lower bound, is a total weight of all the items divided by the bin capacity. If the bin capacity is 1, as we assumed in the previous slide, then the minimum number of bins is going to be the total weight. And we need to use a ceiling function. Okay, maybe I'll write it over here too. I did put it in the note, but let's just write it like this. Okay, so those are some bounds that we have there. All right, so we're going to look at actually 5 different algorithms here. 5 different algorithms. So first of all, we're going to look at the online, and then we're going to look at the offline. So the online, one approach is what we call the next fit, which means I have an item and I got to do something with it right away. So either I put it in the bin I'm working on, or if it doesn't fit, I introduce a new bin, right? So we call it the next fit. It either goes in this one or it goes in the next one. All right. This algorithm is what we call 2 approximate. What does 2 approximate mean? It means that the number of bins that I'm going to use and the number of bins I really should use if I had an optimal algorithm, to solve this, is a ratio not more than 2. So we call it 2 approximate because it's at most 2 times the optimal solution. All right. Why? Why is it 2? So again, for the other ones, we're just going to cite results. In this case, we can actually fairly easily understand it. So let's suppose that you have 2 items that require separate bins. Okay, why do they require separate bins? Because it doesn't fit. So how much space are you really wasting? Most amount of space you could be wasting is like double what you're using. Why? Because if they were closer to each other, then they would both fit in the next one. So the only reason it's not fitting is because it's half the size. Otherwise, it would go into the same bin together. Okay, so if you repeat this argument for each pair of adjacent bins, right? When am I using a new bin? It's only if it doesn't fit. That means that at most it could be twice as much, because otherwise they would fit in the bin together. So what we're saying is at most half the space is wasted. Okay, so this algorithm, it's not considered that good. 2 is not considered that good, but that is the that's the cost. That's the error bound of this algorithm. We call it 2 approximate. Okay, and we have some code for it. So here's some code, right? So the code is fairly easy to follow, right? Basically, we're going through the code 1 item at a time, and we say as follows. It should remind you a little bit of knapsack, but it's not exactly like the knapsack. Okay, so here's what we do. We go through the items 1 at a time, and we say, if the weight of the particular item is bigger than whatever space we have left, this is short for remaining capacity, then we need a new bin because it doesn't fit. And this is a next fit algorithm. And the remaining capacity of the new bin is the capacity of each individual bin, which in our example is 1, but it depends on the problem, right? And then what we do is we reduce the capacity by weight. Okay, so notice how we're doing this here, right? In this case, we're creating a new bin. The remaining capacity is now set to full capacity. And then down here is when we decrement it and we say, okay, reduce the capacity by the cost or the weight of this item. All right, we have some questions here. bin space, right? We're saying that the amount of the number of bins that we need is at most double the number that we would optimally need. In other words, the approximation will come up with a number that is no more than double the optimal. So can anyone tell us the time complexity of this algorithm relative to the number of items?
O of n, go through every
As
item.
O of n, right? Because it's a simple pass through the items and very simple code, right? It just says, if there's no room in the current one, introduce a new bin and use that. Notice we never go back to an old bin. That's why this is a 2 approximate, which is not considered good. Okay, other algorithms are going to be better because we can revisit old, right? So imagine that. If you imagine you're packing suitcases and you say, okay, I'm looking for my diving uniform, right? The diving uniform is full body, comes with some snorkel, some, an oxygen tank, and all kind of mask, right? Well, it didn't fit into the suitcase, so I need to introduce a new suitcase. In the meantime, you got a lot of space in the old suitcase, but you send that suitcase along because you can never go back to another one. So all your socks and undergarments and so on and so forth. Again, this particular problem is assuming they are all, no, not that all items are the same size. No. All items are different sizes. I mean, not necessarily different. They're all different sizes, right? The bins are all the same because this algorithm says next fit, okay? So this one says next fit, okay? We're keeping it simple. I'm not saying this is the only approach. This is the only approach. All right. Next approach is called first fit. What does first fit mean? You place the item in the first of the K bins used so far, right? So we're not just looking at the current bin. We look at all the bins that we've used so far and say, do I have room anywhere? Only if it doesn't fit do we start a new bin, okay? So again, next fit is I can only look at the current one or I introduce a new one. I never go back before the current one. Here, I look at all the bins I have so far, right? Everyone see the difference? So what's the time complexity in this case? What's the time complexity? N squared. Why is it N squared? Because for each item, I have to look at all the previous items. So we have our most famous sum of this semester, right? The first time I have to look at, well, the first time I look at no previous ones. Then I look at one previous one. Then I look at 2 previous ones, and so on and so forth, right? So it could get up to like something like this. Okay, so that's where that N squared comes from. However, it can be reduced to N log N. Why? We can use a binary search tree. Okay, so let me explain why you can use a binary search tree. So each of the bins has an unused capacity. That's what we care about, right? We don't really care what's in there. We care about what space is remaining. So each bin has an unused capacity, right? So one unused capacity might be, there might be 0.6 remaining, and another one has 0.3 remaining, and another one has 0.7 remaining, right? So you imagine having a binary search tree with all those numbers in it. And let's say we have an item that is 0.4. So what do? You look through the binary search tree for the first number you find that is bigger than 0.4. It's not going to fit in the 0.3. You find the first one that's bigger. So you start at the root and you say, oh, the root was 0.3. So you go to the right and you find 0.35. Then you go to the right of that, you find 0.4. 0.4, that's good. I'm going to use that. Okay. However, how long will that take with a traditional binary search tree? How long does it take to find something in a traditional binary search tree? Well, log n is average case, but what about worst case? O of n. All right. So if I do O of n times, that comes out to be n squared. So that's not necessarily so good unless I use a balanced binary search tree, a BBST. Right? If I use a balanced binary search tree, then that log n is no longer just average case, it's worst case as well. So I do that n times, I get down to n log n. Okay, so that's sort of cool. All right, so
Professor,
yes, Ilma,
is it the same as contiguous memory allocation?
is this the same as contiguous memory allocation? I mean, there's overlap, right? So if, yeah, this, you know, you're remembering this from our operating systems, which
Yes.
course? Yeah, so
Operating-
in operating system, you have a similar issue, right? We got someone requests 100 units of memory, 100 bytes. Where do I put that? So I could,
First fit, best fit,
yeah,
worst fit.
right? Yeah. In operating systems also, sometimes you have the issue, you have to swap out things of memory into secondary storage. But yeah, this applies to operating systems as well, right? Allocation of memory, right? Where do I put something? And what do I do if I have a choice, right? So I need 400 bytes of data. And I have a choice. I have a 500 and I have a 600. Which one do I use?
500.
Interesting question. There's no one right answer to that. Because if I use the 600, now I have 200 left over, it's more likely that I can do something with the 200 than the 100. So I'm not taking a stand here. I'm just saying, you know, people do research on that. Okay, you could probably use, it always helps to have statistics, you know, what's the likelihood that I'm going to get something that's 100, you know, so that could influence it. All right, last important point about this algorithm is our error bound. So our error bound in this case, using the first fit approach, is 1.7 compared to the 2 that we had over here, right? So it's saying by using a more involved and more expensive algorithm, right, I can get an improvement. I can get an improvement, right? I can say it's only going to be 1.7 off, which may not sound like a big deal, but imagine that your bins are trucks, and trucks require truck drivers, and trucks are expensive and they require insurance. So the more trucks you need to take care of your shipping needs, that's expensive. So you want, every little bit counts. So that's why companies will pay computer scientists to have good algorithms, because it really makes a difference in the bottom line. It's worth paying good computer scientists. We can also do the best fit. Okay, so this is what Ilma was getting at. There's a best fit approach, which says, okay, I'm going to look at the previous ones and not just find something that works, but which one is the best fit. The best fit means it most closely uses the remaining space. So in the example I gave before with the 500 and the 600, it would use the 500 because it says the 400 is using more of that 500 than the 400 would use with the 600. A similar idea over here, right? Of all the choices, we look at the one that fills up the remaining space the most, all right? So this is also, looks like it's going to be n squared, because I have to look at all the previous bins to figure out which one's going to work best for me. I need to do this n times, one for each item that I need to pack into the bin. So that comes out to be n squared. Once again, if we use a BBST, a balanced binary search tree, like an AVL, like red, black, right? Various trees that we talked about earlier this semester, we can get it down to n log n, because we get our worst case of n down to a log n, and we need to do that n times to get n log n. And the error bound for this is also 1.7. Okay, so not such a difference from the previous one. Now we look at offline. Okay, offline means what? It means we have all the data up front. So let me give you a sort of a real life scenario for this, right? So let's say during the day, they prepare all the packages that people order, right? So let's say you're a Walmart. So let's say from 9 to 5, the people work in the warehouse and they pack the boxes. So they know exactly what boxes they're going to need. And then the shipping crew comes in at 5 o'clock at night, and their job is to get it into the trucks. So they can run their little algorithm there. They know exactly how many boxes they need to ship, and they do it like that. So that's offline, right? We're not creating new packages as we go. They've all been determined with their sizes. All right, so what we do here is something to help us. We sort the items in non-increasing order. That means like decreasing order, except it admits the possibility of duplicates, two things of the same size. All right. So let me give you an analogy here. It's like when you pack your suitcase, what do you pack first? You pack your, let's say your toothpaste and deodorant, or do you pack your dresses and suits and big klutzy things?
Big things first, and then
Big things first, right? You put in the big things first, and then you utilize the space between the items, right, to put in your toiletries and your socks and the little stuff, right? So that's how you're supposed to pack. So someone said, let's make an algorithm out of that, right? Sort the items in non-increasing order. So that's like a decrease when you're going to get the big items first. And now we do a first fit, okay? So you look at the things that you had already. You find, as soon as you find something that fits, you stick it in and you move on to the next item. All right. So again, this could be O of n squared rather. But if we use a BVST to help us find the first fit more efficiently, then we get it down to n log n. And look at our new error bound. Our new error bound is on the order of 4/3, right? So compare that to 1.7, right? 4/3 is more like a 1.3 plus some kind of constant there, okay? And we can do a little bit better than that, right? So again, that's what people do. They write journal articles and they show how they can reduce the bound. And this comes out to be about 1.22, which is better than 1.33, all right? Why does this algorithm not work for the online version?
I mean, you can't sort the stuff till you have all the
You
stuff.
can't sort the items till you have them. That's not entirely true, because you can take data and then as you get them, you insert things, but it's not. You can't rely, the problem is you don't have the biggest up front, right? So yeah, you can do some kind of sorting as you go, but you may not have the biggest until the very end. So the whole concept of the decreasing doesn't really fully work, okay? Online, you could have a sort buffer, okay? So that's a good suggestion, which is, you can take, it's like almost like a hybrid, right? You're taking what you have so far and you sort that. And then you always, you maintain a heap. Yeah, and you always make sure that whatever you have is, the biggest things there. All right, so this is a first fit decreasing, and we have the best fit decreasing. Basically the same thing as the previous slide, we sort up front, but instead of just taking the first bin for this largest item that I have, the next largest item, I look at the one that's going to best utilize the remaining space, try to, finish that off, and that's good. All right. Now I should make a comment about this and this. Both of them require sorting. By the way, it's interesting that first fit and best fit don't seem to be that different, right? So we saw that over here, first fit, best fit about 1.7, and then over here, first fit and best fit also similar kind of bounce. So going through the extra headache to try to find the best fit didn't seem to improve things that much. Yeah, so here's something we've talked about many times in our class, which is sorting. What sort should we use when we say sorting?
Quick sort?
Okay, why do you say quick sort?
because it's one of the best.
So can we quantify that? So when is it good? What makes it good?
If
I'm not disagreeing with you. I'm just, we need, at this point, after analysis of algorithms class, we can talk more specifically about different sorts. So what's the average case? What's the worst case?
average case
Yeah,
is
go.
n log n, and
Okay,
worst
so-
case n squared.
All right, so you're right. But so first of all, you have a worst case that's n squared, so that's not so good. Why is it better than merge sort? Why are you saying it's better than merge sort when merge sort is worst case n log n?
Because merge sort requires more space.
Okay, good. It's an out of place. It uses auxiliary storage. It tends to be implemented recursively. I mean, you can do quicksort recursively as well. The recursion has its own expense. So there's a lot of, there is definitely expense. I don't know if anyone remembers from their assignments what they saw when they compared the merge sort to the quicksort, which one, did better in practice. That's a interesting question. I don't recall the exact results that we had. All right, but can we do better than that? So are there opportunities here for something that's better than quicksort?
Radix sort,
Radix sort. Okay, and why did you say radix sort?
because its time complexity is linear.
Okay, it can be linear, in the number of items if the number of digits is fixed and each digit is in a fixed range. So remember, these are decimal numbers. So you just have to be sure that the decimals are not, arbitrary precision, right? If each weight or size is, let's say, a 2-digit decimal number, and that's it. So radix sort will be very appropriate. And that way the sort part will be order of n. And then all we need to worry about is making sure we've got a good balanced binary search tree. All right, so those are some considerations here. All right, we move on to our next problem and our next approximation algorithm. So our next problem is one of the most famous NP-complete problems out there. It's called the traveling salesman problem, or TSP for short. And the basic idea is you start at a vertex, you visit all the other vertices, and return back home with minimum cost. All right. So what is cost here? Well, cost could be a lot of different things. It depends on the problem. It could be the number of miles that you drive. It could be the time it takes, how much gas is used, the money spent, tolls. Maybe it includes how much you have to spend on hotels. Whatever the cost metric is, right? You want to minimize that cost. The question is, how do you do this? And a optimal solution, the best that we know of, is going to be n factorial time, maybe even if factorial times n. All right. So here's our approximation algorithm. Okay, everyone get this? All right, we start at whatever vertex we're starting at, and we construct a minimum spanning tree using Prim's algorithm. So remember, can anyone remind us about the different strategy between, let's say, Prim and Kruskal? How would you summarize that? So if you needed to give a one sentence, right? So you're in a job interview and they took analysis about them. So yeah, did you learn about minimum spanning tree? Yeah, I learned about minimum spanning tree. Well, what algorithms do you want to learn about? Prim, I learned about Kruskal. Very good. So how would you summarize that? So in Kruskal's algorithm, right, you sort the edges in increasing order, and you repeatedly take an edge. If the edge is needed to combine two different components, then you use that edge to combine the components. If the edge combines two components that are already combined, then, or it's within a component is a better way to say it, then you throw it out. You don't use that edge. And you continue. In Prim, we start with the vertex a little bit like Dijkstra. You start with the vertex here, and you find the vertex in the other set that is closest, and that becomes part of your first set. It gets removed from the second set. So you're always looking for the closest vertex in set 2 to a vertex in set 1, right? So we are going to use that Prim's algorithm. So you start with the vertex 1, we find something in the next one, and so on and so forth, right? So we're building a minimum spanning tree. What does minimum spanning tree have to do with anything here? The answer is because it helps us sort of figure out the order in which we want to visit vertices. Because if they're close together in the minimum spanning tree, that means they're sort of, in order of what we want, okay? So this is very important here. The algorithm is 2 approximate. What does 2 approximate mean?
That you only get half as good as a pot, like or worse, half as good.
So it's right. It's, in other words, the cost that we're going to get is at most twice the optimal solution. So if we could really solve the traveling salesman in 100 units of cost, well, the worst this is going to do is 200. All right. So the reason for that, if you want to sort of sketch of a proof, is imagine if we had to return to the vertex after each vertex, right? So now we're sort of doubling the cost in each case. Okay, so it becomes like double. All right, this is a very important qualification, though. When do we say that it's 2 approximate? If the triangle inequality is satisfied. Okay, so in the upper right-hand corner, I remind us what the triangle inequality says. It says if I have 2 sides of a triangle, then I am better off going on the third side, right? The third side, the direct route. Okay, so that's called the triangle inequality, right? So then this approach is going to be good because it's assuming that if I have, things that are close to each other, then going, direct between them is preferred. In reality, is this true? So would you say that the triangle inequality is satisfied in real life?
Yes and no.
Yes and no. You've been in this course for too long. All right. So if we're talking about geometric distances, if that's what the costs are, they're actual miles, then the triangle inequality will probably be satisfied, right? The shortest distance between 2 points is going to be shorter, if you go directly than if they go through some intermediate point. But we know that things don't always work like that. For example, when it comes to speed, right? So if I go on this local road, I might be able to go only 20 miles an hour. So it's a farm road, right? One time this is like 10 years ago, I somehow had programmed into my GPS to avoid highways because I had taken another trip and I wanted to avoid a particular highway that's always backed up. So it remembered that setting, and I was like in upstate, and it was taking me through all these back roads with all the deer running around, saying, why is it taking me this way? And it was saying that it's going to get me there. I was some crazy hour in the morning. I was saying, why is it going to take so long? I didn't understand. Then I realized it was avoiding highways, right? So if it's about time, right, we may go out of our way because then we get onto the highway where we can go 50, 60, depending on where you are, 70 miles an hour, right? So you can get much better speed. So the Euclidean distance is not always operative, right? So this particular algorithm assumes that the triangle inequality is in place, and therefore, relative proximity is going to help you in this case, where it wouldn't necessarily do that if we don't have a triangle inequality. Okay, so once you get your minimum spanning tree, let's say in this picture here, so what's your minimum spanning tree? The green. The green is the minimum spanning tree. So then you need to do a pre-order walk. What is a pre-order walk? So I just talked about pre-order in my discrete structures class. So if you're starting at A, what's the pre-order? Well, you need to, it's a pre-order. So you get root, then you start on your subtree. So you go to B, You go to E. From the E, you go to C. I can't go any further. I go to G. I back up. Can't go any further. I go to B. Can't go any further. Go back to A. Can't go any further. Go to D. Go to F. G. G is not part of the tree, so I don't need to do that, and I'm done. All right. However, this particular picture, it shows you the minimum spanning tree, but the Euclidean property is not satisfied. Does everyone see that? Can someone give me an example from this picture that the Euclidean algorithm is not satisfied?
Two adjacent edges are of the same color.
Yeah. Going from D to E takes longer than going from D to F to E.
Okay, so if I go from, right, so that's a good example. D to E is 15 and DFE is only 14. Okay, so that's one example. Here's another example. Going from C to E is 5 and E to G is 9, that makes 14. And what's the cost of going from C to G?
Infinite.
It's infinite, right? You're not even thinking about it because you don't see it. So Ellie pointed out a good one that was staring you in the face. This one doesn't stare you in the face, so it's easy to miss, right? So remember, the edges that aren't there are infinite. If Euclidean distance was operative, then it would be a complete graph, and every every edge would be just the Euclidean distance. All right. Okay, so that's our second problem. One approximation algorithm for that. Okay, it's certainly not the only one. By the way, can someone come up with another approach that's greedy? I'm not saying it's necessarily good. What would be a greedy approach to a traveling salesman problem? By the way, this is also greedy. How is this one greedy, by the way?
It's greedy.
Greedy at least in one way, maybe more. What?
Due to minimization.
Well, what do you mean by that? Where in this approximation algorithm, which bullet? Which bullet has greedy in it?
Minimum spanning tree.
Well, minimum spanning tree by itself isn't greedy, right? Minimum spanning tree is a problem. So greedy is a term used to describe an algorithm. So Prim's algorithm, correct. Prim's algorithm is a greedy approach, right? So therefore, if TSP approximation is using Prim, then this is a greedy algorithm as well. One could also argue that once you get the MST, you're using a pre-order walk, right? You're choosing things that are closer within the minimum spanning tree. That's part of the pre-order, right? You're going sort of, in distance order from the root. So that could also be kind of greedy, but Prim we know is greedy for sure. All right. So why did I just mention the greedy part? Oh, so can someone give me a more simple greedy algorithm for TSP?
I always take the shortest path to the next city you haven't visited.
Okay, so basically you take the shortest edge, right? So if I'm at vertex, sort of like Dijkstra, I mean, I guess it's a little bit like Prim, but it's more like Dijkstra, right? So if I'm in vertex A, as in this problem, I look at all the neighbors and I see which neighbor is the closest, and I do that, period. Then I go, let's say I pick D, and then from D, I look at all the neighbors that are, which one's closest that I've not been to yet, and let's say that's F, right? And then actually we have the picture here. So if I'm on A and I pick the closest is going to be D. If I'm in D, I look at the closest, it's going to be F. If I'm in F and I pick the closest neighbor, it's going to be E. If I'm in E and I take the closest, so it's going to be C. Okay, if I'm in C.
You stuck potentially?
Well,
like if the closest was
okay, hold on. I'm not stuck, but I'm also not optimal. Okay, so if I'm in C and I need to take the closest, well, I already did this 5. So my only choice left is the B. And now, well, I'm not ready to go home yet, right? Because I have to, you're always checking, right? As long as I have the right number of vertices. So where am I going to go now? What's the closest unvisited vertex?
G.
G, correct. Okay, someone was keeping track. Good. So G has not been visited. So I'm going to go from B to G. And then I only have the initial vertex left. So I'm going to go all the way back here. So it obviously has some drawbacks, but it is a greedy algorithm. Okay, let's move on to vertex cover. You remember this guy from yesterday? Okay, who can summarize the vertex cover problem? Not the algorithm. You didn't learn the algorithm yet, but the vertex cover problem. Remember, in the vertex cover problem, we want to choose a subset of the vertices such that all the edges are somehow covered by one or more of the vertices, right? So every edge is going to be adjacent to or incident to at least one vertex in your vertex cover, right? So we mentioned an application, real life application yesterday with having security cameras, right? Figure out, what the security camera can see, and you want to be sure that every room, right? So the rooms, the areas are the vertices here, and the edges reflect relationships between, the different rooms, right? What can you see from what room? All right, here's another example. Okay, practical example. So let's say you have a company is, let's say you're going to build a house, right? So you need to get wood, and you need to get this, and you need to get that, right? You need all kinds of supplies. So the contractor is going to order from different vendors, right? They're going to order the supplies. But the way the supplies work, it's not as simple as, okay, I need 100 wood beams, and I need 10 pieces of sheetrock, and so on. They sell it in packages, okay, in packages of different stuff. Why do they do that? Because that's what they have. So they want to get rid of their excess supply. So they bundle it up. You get a better price that way. Fine. So you want to order from the different vendors in such a way that you're going to cover your needs. So you're going to land up getting more than you need because you don't necessarily. I'm sorry. I'm describing the set cover problem. Vertex cover. We'll leave it as is, but they're obviously related. Okay. So how do we solve this set cover? So one possibility would be, okay, can I do it with one vertex? That doesn't work. Can I do it with 2 vertices? And if I use 2 vertices, which 2 vertices do I use? And you gradually increase the number of vertices, but that's a kind of exhaustive search, very expensive. So here's our approximation algorithm. Get ready for approximation algorithm. Okay. So we start with our empty set of vertices. This is going to be our set cover. And we take all the edges and we pick an edge from the set. By the way, no particular order, by the way. And we add U to the vertex cover, and we add V to the vertex cover. And then we say, well, what edges did we just implicitly take care of, right? So let's say in this graph, let's someone pick an edge.
2.
2 is not an edge.
Sorry, 2.
1, 2. Okay, so Cheng wrote 1, 2. So we take this edge at random. Okay, we could possibly improve that, not make it random. We could sort them by their degree, might be a good suggestion. Okay, so that would add some greediness into it. Okay, so what we do is we take an edge and we add 1 and 2 to our vertex cover. And then we get rid of any edges that are incident to that. Okay, so we're going to get rid of this, going to get rid of that and that. Okay, so remove all edges from E that are incident to U and they're incident to V. Okay, and we do that as long as there are no edges. Okay, So we're going to need to get rid of another edge. So we got rid of this one, we got rid of that one, got rid of that one, got rid of that one. So someone pick a remaining edge. I see 4 remaining edges. So Cheng, you want to pick another one? 3, 6. Okay, so we take 3, 6, which means that both 3 and 6 are now in our vertex cover. So we have 1, 2, 3, and 6 in a vertex cover. And we get rid of this edge. We get rid of this edge. We get rid of this edge. We don't get rid of this. Oh, no, we do get rid of this edge as well because it's connected to 6. So now all of our edges are gone. So our vertex cover is 1, 2, 3, 6, as opposed to the optimal vertex cover, which is 1, 3, 5. So that's our algorithm. And our time complexity is, well, let's look at it. So the outer loop is O of E, right? We need to remove the edge for the neighbors. So we need to look at all the neighbors, right? And we need to do that. So we're doing E times V, but in reality, the total cost is going to be O of E. Why? Because as you look at the neighbors, you're getting rid of all those edges. So the total number of activities is E. It's like almost like an amortized kind of analysis. Okay, so it's pretty efficient algorithmically compared to doing something that's exponential time. You know, the question is how good is it? So that we don't have here. Okay. All right, we have one more approximation algorithm. Okay, remember set cover. What is set cover? Set cover is we have a big set, a universe set, and we have some subsets. And the question is which subsets, they're not a partition, okay? So they may be overlapping. So which subsets could we put together to get back our universe? Right, so let's go back to the example I started to give you a moment ago for vertex cover, and it's really set cover, right? So again, I'm ordering supplies, but the supplies, I don't get to order exactly what I want, right? It's a package. So this package comes with some wood and some sheetrock and some nails and all different stuff. And, you know, there's another package available. So I want to know which packages do I need to order, packages of stuff do I need to order so that all my needs in the universe are satisfied, right? If I put it all together, I get what I want, right? So we call that a set cover. Set cover is an NP complete problem. And the question is, you know, how can I approximate that, all right? So before we come up with the approximation algorithm, I'm going to introduce you to another version of the problem that's a little bit more complicated, right? It's called a min cost set cover. What does that mean? So imagine that we have not just a bunch of sets, but each set has a cost with it. In other words, the cost of this set is 20, and the cost of this set is 10. The cost of this set is 5. The cost of this set is 100, right? So just like in the example I gave, right, you have to pay for the set. So you want to pay for the minimum cost, right? Keep in mind that this problem is the same as this problem if the cost of each set is the same, right? The cost of each set. So if we make the cost of this set 1 and the cost of this set 1 and the cost of this set 1 and the cost of this, then they all have the same cost. So it becomes the regular set cover problem. So here is a algorithm. Okay, the algorithm says start with something that has nothing in it. And you look at all the subsets, and you take the subset that minimizes the cost divided by how many new elements you get. So remember, what we're trying to do is when we take a set, we want a set that's going to give us a lot of elements, right? So if all the costs are 1, then this is a good bang for the buck. This is a good bang for the buck. But keep in mind that once you start, go ahead.
The set has more elements, that's why.
Well, it's two things. So you want more elements, but you especially want more elements that you don't have. So anyone here trade baseball? Anyone here into baseball cards or were into baseball cards when you were a kid? Right? So, when you buy a pack of baseball cards, it's not just, of course, you don't get to know what's in them, but let's say someone told you what's in the pack, right? So it's not just, how many, baseball cards are you getting for the cost of the pack of the cards, but you want cards that you don't have already because you're trying to get the whole set, all the players from that year. So the same thing over here, right? We're trying to not just, get a lot of elements, but elements that we don't have already. So that's what this thing is saying. It's saying, okay, there's a cost for that subset, but what I really care about is not just the cost, but how many elements am I getting, right? So this is saying, this is the number of elements in the set. And this is saying how many, you know what, I should write this slightly differently. Let me write this slightly differently. The right way to do it would be to write it like that. Okay, so we take the size, right? The difference in the size of the new set minus what I have already, right? This is saying how many new elements am I getting? See that? What do I have in the set minus what I have already? So that difference is what I'm adding. Right, so it's cost effective, right? It's cost effective. So we need to look at all of those, and then we take that set. So whichever one gives me the smallest cost for the most number of elements that I get to add, and we add that subset to our X. Okay, and let's look at the analysis for that. Okay, so actually, before we do the analysis, we have an example. Okay. So here's an example, or universe. I can make it a little bigger, actually. Okay, so here's my universe. Okay, this is not the example from before. And I have 3 subsets, okay? Subset 1 is 4, 1, 3 in it. Subset 2 is 2 and 5. Subset 3 is 1, 4, 3, 2. And each one has a cost associated with it. Okay, so what would we do? Well, we say how many, actually, I have this written out on the slide, so I might as well look at it. Okay, so the first time through, how much bang for the buck do I get for each one? So I have 3 elements in this one, and it has a cost of 5. Does everyone see that? I have 3 elements in this one and a cost of 5. Okay, this one has 10 elements and a cost of, the cost is 10 and it has 2 elements. Did everyone see that? 2 elements, cost of 10, and the third one, so we don't have to go back, has 4 elements in it and a cost of 3, right? So which one am I going to use? Which one gives me the smallest cost per item?
S3.
S3, because it's only 3/4 compared to 1 2/3 versus 5. Okay, so what is my X now? X is all the elements that were in S3, which is 1, 4, 3, 2. Now I do the iteration again. I say, okay, if I use S1 had 3 elements, but I already have the 4, I already have the 1, and I already have the 3. So how much did I get? Nothing. So what is my cost per item? Infinity. Bad. Okay. Second one is the cost was 10 and I only get 1 new item, which is 5. So my cost per item is 10 over 1, which is 10, but that certainly beats infinity. So we add S2 and X becomes 5. Right, I get the 5th item and I'm done. Okay, so that is that. Now, do I have an analysis here? Okay, I'll come back to that other thing. Okay, so when we do the analysis, so whenever you do analysis of an approximation algorithm, there are really 2 kinds of analysis that we could do, right? One analysis is time complexity, which is what we've been doing all semester. And the second question that we have, and I guess you could do space complexity also, but the other question is how good of an approximation, right? So the accuracy or the How good is our approximation? Right? Okay, so it turns out that the approximation is opt times log n. Okay, so opt is the optimal cost, and the overage, how much more than the optimal cost it is log of n, which is very small. So that's actually good. So this is considered a very good approximation. And the basic idea is that each time your approximation gets better. In other words, if there's only one item left, so it's very clear which one you need to take. When there are two items left, so you could be, choosing incorrectly. So you end up with these division by n and then n-1, depending on the number of items left. And if you factor that out, that's the harmonic series, right? I'll just put a note there. That's the harmonic series, right? So it comes out. So that's a very good approximation. Let's go back to the time complexity. Okay, no, where's my code? Yeah. Okay. What's the time complexity here? How long does this step take? It looks like it's order n, right? Because I got to go through each thing, figure out how many it's going to leave me. It could actually be more than that, because if I have to do a set difference, so not only am I iterating over each item, but I'm looking at each item in the set. So I could do this more intelligently, okay? And what I could do is for each set, I don't really keep track of how many things are in the set originally, but how many things remain in the set that I haven't used, right? It's like sort of scratching out the stuff I don't care about anymore. So you basically have like a copy of all the sets, and as you get rid of, you've used something, so you update the sets to say, these are the things I still care about that I don't have yet. And it will simplify this computation, okay? So let me make a point of that. Okay. All right. I got a typo there. All right, so I want to just point out something here. This is an approximation algorithm. What does that mean? How accurate is our approximation algorithm? Is it accurate? Well, we're saying it could be as much more than log of n off, which means it doesn't always get us the right answer. Okay, so take a look at this. By the way, this is a greedy algorithm, so it's an approximation algorithm, but a lot of the approximation algorithms are greedy, as we've seen before, right? So take a look at this algorithm here. Okay, which one are we going to choose first?
S3.
Okay, so we're going to take S3, and then what are we going to take? We're going to take S2 because S2 gives us 4 items, right? Notice it's carefully chosen, right? So S2 has a lot of items that we haven't chosen already. So the cost of it is 1, let's say, and we get 4 items we haven't done. So we're going to take the S2, and then we take S1 because that gives us the one that we don't have. But if I use the S4 and the S5, I actually get it with only 2 sets instead of 3. Okay, why am I not taking the S4 first? Because the S3 has more, so I seem to be getting more bang for the buck. So you do have to watch out for that. All right, does anyone have any questions?
Professor, for the TSP, why are we using Prim's algorithm and not Kruskal or Bellman-Ford?
Okay, so fair question. So first of all, Bellman-Ford is a single source shortest path algorithm. Understand? So, I mean, you could ask, why not use Dijkstra and Bellman-Ford, right, which are shortest path algorithms, but remember, it's shortest path. Both of those are single source shortest path. So it's like finding the cost from the beginning to that vertex, cost from the beginning to that vertex. And the truth is, you could do that. You could do that, but then, you know, the question is, what's the path? Right. So let's say I find out that, you know, how do I want to go? Well, the other thing is they're going to be overlapping. So you really want to do that. So again, Bellman-Ford and Dijkstra are both single source shortest paths. So they're all about one vertex of importance and how you get from the vertex to other vertices. So back to your other piece of your question, why Prim and not Kruskal? I think the answer is because Prim works on the sort of relative distance compared to what you just got. What do I mean by that? So first of all, how do you pick the next vertex? You pick the next vertex because it's the closest to where you are. How do you pick the vertex after that? It's the closest to anything where you are, but it tends to pick up things that are close to what you just added, right? So Prim is heavily based on what is close to what you just added. And that's good because you want this sort of incremental approach, right? You want to pick up things that are in a relative order because that will give you a good pattern overall. Did that make some sense?
Yes, makes sense.
Yeah. Okay. All right. Any other questions? Are people, are you looking at the old exams? You're getting some experience with that? Why don't we take a look? Let's just take a look at our old exams here. All right, let's just, we have about 10 minutes left. Let's just, we didn't. Okay, let's take a look at this problem here. All right, describe a brute force approach to finding the product of two long multi-digit integers. How would you do that? Am I still screen sharing?
No, we don't see it right now.
You don't see it. Well, that would be good if I screen share. Okay. All right. How do you do that, right? You take each digit in the second one, you multiply it by each digit in the first one, then you repeat that process for the next digit and so on. So what is the time complexity there?
O(n) squared.
O(n) squared, where n is the number of digits. Okay, good. Describe a brute force approach to evaluating polynomial of x. So you need to evaluate each term separately. So if you have a term, I don't know, a1 times x to the n, so you need to find x to the n. That's going to take n minus 1 multiplications, multiply it by the coefficient. That takes another, okay? So you do that for each term. So the first term is going to take n, multiplication, second term n minus 1, third term n minus 2, and so on. If I add all that up, I get n minus 2, I'm sorry, n times n minus 1 divided by 2, or n squared. So it's n squared. Brute force approach to multiplying a pair of n by n matrices. I take each row, multiply it by each column, which is also known as a dot product. And the cost of the dot product is O of n. So what's the overall time complexity?
O of n cubed?
O of n cubed, good. All right, the next question was about n linear equations. We didn't discuss that. That would also be n cubed, but we didn't discuss that. Okay. Sorry, that'll be n squared, actually. Okay. For one of the four aforementioned numerical problems, describe an alternative approach that is better than the brute force. So what can we do to improve number one?
I mean, if we're doing parallel, we could, take each next digit.
All right, so we could do parallel, but yeah, so parallel isn't an option here. I'm not saying you could do parallel, but that's not what I'm really looking for. I'm looking for, without parallelization. Remember Karatsuba? Karatsuba says it's a divide and conquer algorithm. Break up your long integer into two parts, left and right. Break up the other one into left and right, and then you sort of cross multiply. And what he found is that you can do that with 3 subproblems instead of 4, right? So you now have a recurrence that looks like T of n equals 3 times T of n divided by 2 plus O of n. Time complexity is n to the log 2 of 3, which is maybe something like 1.6 or 1.7, right? For a polynomial, we had Horner's method. Horner's method can solve it in linear time instead of quadratic time. The matrices, we had Strasson's algorithm, which turned it into 7 subproblems instead of the 8 subproblems of divide and conquer. So you get order of n to the log 2 of 7. And again, we didn't discuss solving a linear system of linear equations. Can't I navigate? There we go. All right. Okay. How do you find the farthest pair of values in a sorted array?
First and last elements.
Take the first and last. What's its time complexity?
Constant O of 1.
Constant 1. Good. And how do you find the closest pair? So the opposite of farthest.
Go through each pairs and you can evaluate which one is the best.
Okay, so you go through each adjacent pairs and you see which one of those is smallest. And what's that time complexity?
O of n.
O of n. Good. All right, describe brute force approach to find the closest pair of values in an unsorted array of numbers.
I mean, the brute force way would have every number be evaluated next to every other number, which would be
Okay, so that would be brute force, right? You look at all pairs, and what's the time complexity of all pairs?
n squared.
N squared, great. Describe brute force approach to find the closest pair of values in a set of points in 2 dimensions.
I mean, the same thing as the other approach.
Same thing, right? Same thing. We pointed out a slight optimization where you don't necessarily have to do the square root of the distance function, because if you're comparing squares, that's the same as squaring square roots. Right, describe a divide and conquer approach to find the closest pair of values in a set of points in 2 dimensions, right? So that was where you break it up sort of like a little bit like a merge sort. You find the closest pair on the left, the closest pair on the right. But here's the catch. You can't just take the smallest of the two. You have to also consider the ones along the, the boundary. And on the surface, it looks like, well, you didn't help anything, but then you realize they're only for any given point along the boundary, there are at most 6 other points, either on the boundary or to the other side of the boundary that you need to consider. So it comes out to be T of n equals 2 times T of n divided by 2 plus O of n. Solution to that, as we know from merge sort, is n log n. All right, now we have a problem here. Suppose that in a geometry exam, each of the M students in the class is given the same list of N cities around the United States, and is asked to specify the coordinates, longitude and latitude of each city. Okay, grade of A+ is given to the student who has the smallest total deviation of his specified coordinates from the actual coordinates. Okay, so basically we have a bunch of cities. Okay, describe how to determine which student gets the A+. Okay, so let me just explain the problem. All right, so you don't know, you're sort of guessing, right? You're guessing what the longitude and latitude are. Okay, so the question is not what the student should do. The question is, how does the teacher evaluate their answers? Right? So the teacher knows what the longitude and latitude of each city is. And the student had their guess, let's say. They looked at a map and they tried to figure it out. Right, so basically you have 2 lists. You have the students' estimates for the longitude and latitude, and you have the actual longitude and latitude.
So for each, like let's take the first element of the student's list in the first city and find the distance. And you don't have to square root, like I said before, the same optimization can be done, and then just add them up together.
Yeah, so you're going through, let's say, student by student. For each student, you compare your list with that student's list, and you take the difference, okay? And you look at that, okay? You could use a square difference. It doesn't really specify the smallest total deviation, what formula you're using for the deviation, and you do that. Okay, so what's the time complexity there?
O of n times n, where m is the
It
student.
looks like m times n, right? Because you're going to go through, for each student, you need to go through all the M cities. Okay, so with the 4 minutes left, I'm not saying this is something where you would actually use an approximation algorithm, but are there any heuristics you would use maybe to cut this down? Again, m times n is not bad for an algorithm, so you probably wouldn't use an approximation. And also, if you're giving someone their grade based on this, you probably shouldn't use an approximation algorithm either. Think like randomization. Let's say the teacher was running out of time, right? The grade was due in 15 minutes after the exam was over. And they don't have time to do the m times n algorithm. So how might you estimate which student seems to be doing really well? And then maybe you narrow it down to 5 students and you determine which of those 5 students gets the A+. So think like Rabin does. Rabin is our expert in randomization. What happens if you are to take each student and you pick 3 cities from their list? And you look at how close they were for those 3 cities, right? And you see, okay, which of the students did the best on those, 3 sample cities? And you say, you know what? It looks like those students are the ones that have a knack for this. So we're going to narrow it down to the best ones there. And then for those best ones, we're going to actually do the math. Okay, so what's the time complexity now?
Now just O of M, or M's the number of students.
Well, it's first you got to do the number of students, right? Because you're doing a sample for each one. So let's say we're taking a sample of K for each student. So that's going to be K times M. And then once you decide how many students, are in the, finalists, right? So that's going to be some small number times N, because we're saying for those, you actually have to do all the math to really determine who's going to get the A+, right? So it's going to be O of M plus O of N. Okay. All right, so we're going to stop here. Everyone have a great day and a great weekend.
Thanks, Professor. Have a good weekend.
Okay, bye-bye. Is that what it says? Does it say August 6th? Yeah. Yeah, so let's make it August 6th. I'll be putting up the forms, okay?
Hi, Professor.
Sorry. Yeah, what?
I'm just asking for since I see my grade just for assignment some assignment is still be the 0. Is that you
Which assignment number? I can tell you if I graded it or not. Which one?
assignments? I guess. Give me a second.
Well, so this class I've graded through 3, I believe.
3.
1 through 3 is graded. So if you don't have a grade for after 3, that's okay. If you are missing a grade for 1 through 3, that's not okay.
So I'm missing grade for assignment 2.
So there are 2 possibilities. Either you submitted it or you didn't submit it. So which possibility are we talking about?
I submitted
Submitted it using the correct form or not the correct form?
the correct form.
Okay, so send me a message on Slack telling me what day and time you submitted it, and I can look back and which form you used. You should get a receipt from Google. Okay, so Google Forms gives you a receipt.